talk. So our next speaker today, our second speaker today, is Dr. Sendhil Mullainathan. Dr. Mullainathan is the Roman Family University Professor of Computation and Behavioral Science at Chicago Booth. His current research uses machine learning to understand complex problems in human behavior, social policy, and medicine. In the past, his work has combined insights from economics and behavioral science with casual inference tools to study social problems such as discrimination and poverty. He's written on a wide variety of topics, including the impact of poverty on mental bandwidth, how algorithms can improve judicial decision-making, using fictitious resumes to measure discrimination, showing that higher cigarette taxes make smokers happier, and modeling how competition affects media bias. He's published extensively. He has co-authored a book called Scarcity, Why Having Too Little Means So Much, and writes regularly for the New York Times. He's received a MacArthur Genius Grant for his work. Outside of his research, he's co-founded a nonprofit to apply behavioral science, a center to promote the use of randomized controlled trials in development, has worked in a variety of government roles, serves as a board member in the MacArthur Foundation, and is a member of the American Academy of Arts and Sciences. Thank you so much for Dr. Mullainathan for joining us this afternoon.
Thanks for having me. Let me just see if I can get the clicker to work. It worked. All right, terrific. So today I'm going to talk about the power and danger of algorithms. And I have not worked, full confession, in this area of therapy algorithms at all. So I'm going to try and take what we've seen in other contexts for the use of algorithms and try to kind of crudely instantiate it in this area. But I'm looking forward to the discussion where hopefully the ideas resonate and you all have other examples. The example that I wanted to start with was the rise of chatbots in therapy. So I picked this one example, Wobot. I know there are many others. And what's appealing about these is that they sort of do a variety of things. And the chat interface is so powerful because from it, you could say, well, we can track your mood, give you insights, teach you stuff, learn from you over time. And as I have to just start by saying that it's pretty clear that algorithms are very powerful and that these sort of automated or semi-automated algorithms hold a lot of promise to improve our therapeutic efforts. And I think one of the reasons that they are so promising from my point of view is they allow significantly more patient interaction than just sort of humans talking to patients. And to me, that has an equity angle, because putting on my economist hat, if we can lower the price of something, that means a lot more people can get access to it who otherwise couldn't afford it. So on its surface, I think there's something very powerful about this wave of technology. It allows more people to get access. It empowers therapists to do more. It's just generally a good thing. I'm saying all this in a very positive way because what I now want to do is to express caution. And I want that caution to be properly framed. I'm not negative about where this space is headed. I am positive and optimistic, but I want to point out relatively big roadblocks we face that we need to deal with, lest something go pretty wrong. Okay, so let me tell you an example, use an example from the past to illustrate the kind of roadblocks we face. So I don't know if many of you have interacted with this. This is called Tate Tweets. I think it's been taken down. This is a bot that Microsoft put out, their AI team put out, to illustrate as sort of a victory lap of look how good we've gotten at natural language processing, about algorithms able to speak like humans. We've gotten so good, we're going to put this algorithm, give it a Twitter account, and let it interact with human beings. And it was it was pretty cool. It started off with some pretty interesting things, and people would have conversations with it. And in a short amount of time, though, stuff started to go a little sideways. For example, Tay Tweets started saying some slightly crazy things, such as Bush did 9/11. That was a little sideways. I say that because it got much worse. Before you know it, it was denying the Holocaust. And as you can see, as one person put it, all this happened in a 24-hour period. It went from being reasonable to just outrageous, beyond the pale, all in this small little period. So what went wrong? How did this thing screw up so badly? Well, the first thing you have to understand about what went wrong with Tay is that you have to understand that the engineering worked fine. We're all used to having software fail on us. I am sure many of us have spent countless hours of our lives looking at a screen, the blue screen of death, or a spinning wheel that's not, software crashes. We know that. That is not what this was. To understand what is going to go wrong with algorithms, we have to stop looking at the algorithm. The algorithm here worked fine in the sense that, in the narrow sense that, the engineers were tasked to build an algorithm and they built it correctly. It did not crash. There was no freezing up, no failure to give a response. In fact, it worked so well that the Chinese version of this had been working since 2014. The New York Times wrote a very nice article about it. And Tay was introduced to simply show the world that success. So what then did go wrong with Tay? To understand that, you have to understand that algorithms such as these are not built like other algorithms. These machine learning AI algorithms are not built by just having coders in a room code something up and seeing that the code executes what you want. A crucial part of these algorithms is that they interact with data, the training data. The code is only a part of it. The resulting output is how that code interacts with the data to then produce the behavior we see. Very rarely is the problem in the original code, and I'll give examples of that later. Very often, the problems arise in the data. And let me explain what I mean. These algorithms work on the data they're given. So usually what people do is they'll take this training data, keep some aside that the algorithm has never seen, and then do out of samples tests and say, yeah, the algorithm worked. So they tend to work on data that looks like the training data. In other words, these algorithms are trained on one type of data. They tend to work when they're put into situations that resemble the data they've been given. And that's the whole point. That's the methodology. But of course, the problem with Tay was that it was trained in an incredibly friendly environment. It was trained using corpuses of data that look like this. But then what did you do? You put it out onto Twitter and exposed it to an environment much more like this. You can see the deployment environment is so different than the training environment, failure is almost guaranteed. And this is the first lesson I really want to convey. Algorithms only work on data they were trained on. They do not work in environments that are very different. So when you look back at chatbots such as Wobot, all these things, what was the training data for these? How does that resemble the patient context you're putting it in? Do we even know? The typical machine learning playbook ought to scare us here. It's typically, I've got an algorithm from some training data that works okay. You know, it does something, but that's okay. I'll deploy it. And in deployment, I'll get better data closer to my deployment to improve. This works well. I mean, this is how you can launch a recommendation engine that tells you what recommendations to give you on movies. And the early recommendations have some screw ups, such as life. This is a terrible idea if this is how you're going to launch therapy chatbots or other things in this space. That means that we need to have a lot more scrutiny into the training data for these algorithms. Okay, that's lesson one. Lesson two, there's another kind of problem with training data, which we have seen many times in the last 4 or 5 years. Let me show you an illustration of this on Google. This no longer works, mainly because these results were made so public that Google then said, we got to fix this. But for a while, if you searched on unprofessional hairstyles, these are the images that you got. You'll notice a common theme on the so-called unprofessional hairstyles. It's not just on searches like that. For a while, if you searched on Google for nurse, this is what you got. And you'll notice a common theme here. If you searched for CEO, this is what you got for a long time. Again, you'll notice a common theme. Now, as I said, these examples have gotten common enough that now people have gone back into the algorithms to try to fix them. Now, if you search for CEO, you get something more like this. But what all of these illustrations show is that the training data for Google search is the corpus of images that were out there. The corpus of images that were out there had biases, our biases, about what a person looks like, what a CEO looks like, baked into those data sets. So Google, the algorithm, simply just taking the data and replaying it back to us, inherited those biases. And that's the second lesson. These algorithms, when they're built on biased data, tend to reflect those biases. Let me show you an example of how extreme this can be. This was a thing, I don't know if many of you have seen this on Twitter. This was an illustration someone did with some facial reconstruction algorithms. If you look at this image and you say, who is this? I think we all know who that is. If you run this through certain reconstruction algorithms, whom you get is this. That is not who that is. But you'll notice there is a notable characteristic about the person on the right that's different from the person on the left. One of the tweets I really liked most about this was somebody who had done this across a variety of images. And you'll notice the common theme here of the reconstruction errors. If algorithms, facial recognition algorithms, are trained on corpuses of white people, then when they go to reconstruct faces, they will reconstruct them as white people. They will not see disadvantaged groups, minorities, literally, because they didn't see them in the training data. I'll give you a last example for language that was very compelling. So this was a very influential paper that showed what happens when we train algorithms on large corpuses of the kinds of language data that are often trained on. So here what they showed is, let's take the algorithm, train it, and have it do a bit of analogical reasoning. So if we say to it, man is to woman as king is to what, kind of cool, the algorithm on its own learns man is to woman as king is to queen. That's pretty cool. That's what it learned from the data. But if we say man is to woman as physician is to nurse, wait, it's learned a weird gender bias. If we say man is to woman as brilliant is to lovely. So these are the biases in our language. This is how we as human beings tend to speak and have these biases in these corpuses of data. The algorithm trained on it, well, inherits them. And that's the problem. Algorithms inherit the biases from the data they were trained on. This is especially problematic since language models are often trained on general corpuses of text, including the web. That's the question you should ask yourself. Is this the kind of biases we wanted to implement? Now, these algorithms scale up, and that's amazing, but it's hardly an accomplishment to scale up our biases. Let me end on one example. The example I want to end on is a detailed study we did last year, and it'll show you the third kind of problem that we can have with algorithms. This is around care coordination programs. Care coordination programs, in a nutshell, are programs that are used to target people who need extra resources. And in these to get people into these programs, we tend to use algorithms, and these algorithms are used at scale. Hundreds of millions of patients go to them to decide who should get into these programs. And the way what these algorithms look for is people in need of extra care. So what we did is we audited these algorithms for racial bias. And what we found for these scaled algorithms is a huge amount of bias. On the x-axis here is the algorithm's risk score from one of these commercial algorithms. On the y-axis is how sick the people were after the fact. And the two curves are black and white. Now, one way to understand this curve is that at this auto-enrollment level, 28% more chronic illnesses for Blacks who are auto-enrolled than whites. The algorithm was significantly under-enrolling Blacks. If we were to simulate the act of replacing healthier whites with less healthy Blacks until marginal patients are equally healthy, that is, create equity, what we would have gotten would have been to, I'll just walk you through this, and what we would have gotten is to sort of imagine taking these high-risk Blacks we'd like to add more and remove these low-risk Blacks. What we would have gotten, until we got to the same level of health, we would have ended up with, oops, sorry about that. we would have ended up effectively adding we would have ended up doubling the fraction of auto-enrolled Blacks. So what this algorithm was doing was it was counting Blacks as less risky, even though as equivalently unsick whites. So it was really underseeing Blacks. This is a big problem since, as I said, this is applied on hundreds of millions of people. So where is the algorithm going wrong? One clue is in where it's going right. If we did the same exercise, but instead of looking at health, we had looked at cost, we would have found no gap at all. And this is because the algorithm was finding equally costly patients, not equally sick patients. How did this happen? This happened because when the team wrote the algorithm, they said, oh, what are we optimizing? Oh, health. And in healthcare, there's this vague relationship. Sometimes health is cost, sometimes health is health. And here, cost was the easiest to get data. So the algorithm was inadvertently or advertently looking for cost. The problem of predicting costs, of course, is that Blacks and whites do not have the same relation between health and cost. Whites have better access to care, and as a result, for the same level of illness, Blacks cost less. So when you find accurate cost prediction is going to be biased health prediction. Okay, so let me end and just sort of say, the lesson I want you to take from that is that the algorithm did exactly what it was asked to do. We're going back to Tay. It was asked to predict costs, it predicted costs. The problem is on us, is on what we asked the algorithm to do it. These miscommunication here was that we synonymously use costs and health, which is sometimes something we do. These miscommunications, these misformulations of the problem are the source of the issue. So I'll end here by sort of saying the third lesson is algorithms are very sensitive to the objectives they are given. How carefully thought out are the objectives of these chatbots? What are they maximizing? What constitutes as a good success versus a bad success? So I want to end by basically saying this illustrates the power and danger of algorithms. Expanding the scope of resources for mental health, that is terrific. Chatbots and other tools that do that, that is terrific. But that promise can quickly become peril. And it is our job to ensure that we avoid the peril and ensure that we realize the promise. Okay, thank you.